All right, this is our next unit, rational functions. So for today, we're going to take a look at how to find all the characteristics of a rational function. So when you have a rational function, you're going to have an expression in your numerator and your denominator. So we're going to look at all different kinds today. All right, so up first is the domain of rational functions. To find the domain, you set the denominator equal to 0 and solve. And those values that you find for x are what x cannot be. And here's a special note. If your denominator doesn't have any real zeros, so maybe it has imaginary zeros, it means that your domain is going to be all real numbers. So you might want to highlight that. We'll see one of those cases today. Okay, so for part A, here's the first equation. It is 2x over the quantity x plus 2. And we just want to find the domain. So all you need to do is set the denominator equal to 0 and solve for x. So if I do that, I have x cannot be negative 2. I can write my domain using set notation or interval notation. So for set notation, I would say all values of x such that x cannot equal negative 2. And if you think about the number line, you'd have an open circle at negative 2. And when you read it left to right, you'd have negative infinity to negative 2, and then from negative 2 to infinity. All right, the next equation in part B, you want to find the domain, set the denominator equal to 0, and solve. So here we have a quadratic, so see if it's factorable. It is, and a special shout out, please make sure you know how to factor a quadratic when a is larger than 1. You have to make sure you're confident with that. So this quadratic can be factored. I set each factor equal to 0 and solve for x. Now these are the values that x cannot be. For if you were to plug this in for x, you would be dividing by dividing by 0. So again, I can write my domain in set notation or interval notation. And you can see here's how you would write it in set notation. And then if you imagine the number line, you would have open circles at negative 2 and positive 1/3, but everything else would be shaded. So it can be, x can be anything except those two numbers. So again, reading that number line from left to right, here's your answer in interval notation. The last one, part C, if I take the denominator and set it equal to 0, it is a quadratic, so you might investigate if it's factorable. It's not factorable. You can solve it using square roots. So if I get the x squared by itself, I would subtract 9, take the square root of both sides, and that special note up here, if it has no real zeros, then your domain is all real numbers. There's no restrictions. And on all of these, you can see I put the graph next to them, so you can kind of see what does that domain restriction look like on the graph. So for part C, you can see there's no restriction. It goes across the graph from left to right. However, on part B, you can see those vertical asymptotes at negative 2 and 1/3. And then on part A, you can see that vertical asymptote at x equals negative 2. And spoiler alert, we're going to talk about vertical asymptotes next.